Hi everybody, welcome to Calculus 2. This section is about volume by slicing, or more particularly, the disk method. So, what we're trying to find here is we're trying to find the volume. And to find the volume, there are two different ways to do it. In this section, we have the volume by slicing. The next section is the cell method. So the disk method and the cell method, pretty much. Right, so what we do to find the volume, what we're trying to find is the volume of a shape like this. So in that case, we will cut that like slide bread into a bunch of slides. The more slices we have, the better the approximation is. So we take the number of slices, let that go to infinity. In that case, we have the volume of a piece of the whole thing. Right, so pretty much that. We just cut that into slices and then find the volume of all the slices, add them up, we have it. And when we add them up, that is the integral sign, the definite integral. Right, so let's look at the first example. Suppose we have a solid bounded by the curve y equal to x squared, y equal to 2 minus x squared in the xy plane, and then we will rotate that to form a semicircular disc. Right, so first of all, we have y equal to x squared. It is a parabola. I'll open up. And then we have y equal to 2 minus x squared. Parabola open down. When x equal to 0, y is equal to 2. So we have those two curves. Now if we put that in 3 dimensions, we have the 2 that's y equal to x squared, and the other one that is y equal to 2 minus x. And then from that we form a semicircular disc above it, and then we're trying to find the area, the volume of that region. So first we have to find this distance here, which is the diameter, and then we form a semicircular disc above it. This is the diameter. So that is equivalent to this one here. So just like the last section, the upper function minus the lower function. So that one is the diameter is equal to the function above, which is 2 minus x squared. And then subtract the function below, x squared. So that gives us 2 minus 2x squared. So that is the diameter, the whole thing. Now, if we want the radius, we cut this in half. So, if we talk about the radius, it's going to be that distance. Right, now we're going to form a semicircular disc above it. So if we want the area of one disc, the area of that is semicircular, right? So it's going to be half of the whole area of a disk. So we have the area of the cross section of a semicircular disk, and then we need the width. The width will be very small. Think about that. If we have a very small segment like this, so the width is just going to be delta x. So we're going to have a slide like that. So we got a slide from it. So there's the width, and the width is delta x. Bottom line is, if we want to find the volume, it is going to be the integral. The x values here go from -1 to 1. And all we do is just add all of the cross-section area times the width dx. And the cross-sectional area is 1/2 pi r squared. The radius is going to be 1 minus r squared, 1 minus x squared, and then square again. That gives us the volume of that region. But as mentioned before, that's nice and all, but we focus on this section is the focus on this section is on the disk method and the washer method. Right. So pretty much what we have, what is the disk method? So this method, suppose f is continuous function that is greater than or equal to 0, so non-negative function on an interval from a to b. So we know certainly the interval of integration, the limits for the integration. Let script r be the region bounded by the function and the x-axis, and the line x equal to a and x equal to b. So if we talk about this in the graph, r go from a to b, and then bounded by the function and the x-axis. So this is the region R. Now what we're going to do is we're going to take this and we'll revolve that region R about the x-axis. So we just spinning it around, so it look like the shape will look like this, that one, and that's called the solid of revolution. So when we're revolving the function about the x-axis, we have a volume, and the volume is given by pi f of x squared dx. So where's that formula come from? So think about this. We have the radius, we rotate about the x-axis, so from the axis of rotation go outside, we're going to have the radius. That's why I write different r. The radius is r, the region is I call that the script r. So we have the radius, the distance from the axis of rotation to the edge of the region, and then we rotate that. So, and then when we rotate that radius, we're going to have a disk. So a disk will look like this, right? I'm going to draw in 3 dimensions though. So we have a disk. So one slide, and the disk we have the radius, and then the width of that, the width. So we're going to rotate that whole thing. There's the width of the x, and so the volume. So the volume of this is the cylinder. If we turn it upside down, the volume of the cylinder with the radius r and the height h, the volume equal to pi r squared and then r squared and then h. That is the volume of a cylinder. Now this is also a cylinder. If we turn that sideways like this, we have the radius, the base, and then the height is delta x. So the volume of one cylinder or one disk is V equal to pi r squared times dx, the width. So for one slide that, if we want the volume of the whole thing, we're going to add the integral to it, and we add the volume of all of those cylinders, of all of those disks, and we should have the volume. So that's why we end up with this. So in general, the volume will be just we know the limit from a to b though, and we have pi r squared and then the width I don't know why we don't even need that bracket. So the radius square and then times the width of the disk. So pretty much that. Let's put the square on the outside. Right, that better. So we need the radius and the width. The width is dx, so we just need the radius pretty much. And we'll just do that. That should be simple. Right, so let's look at the first example. Let R be the region bounded by the curve f of x equal x plus 1 square. The x-axis, the line -1 and 1. So let's see the graph. X plus 1 square right. So pretty much just the standard parabola, but move 1 unit to the left. So we draw so this is y equal to x plus 1 square. So we have the function, and then the line x equal to -1. So here's -1 and x equal to 1. X equal to 1 is the vertical line. And so we have this is the region R. Find the volume of the solid revolution obtained by revolving this about the x-axis. So we will rotate about the x-axis. So when we rotate this point here, we move to about, say, here. And then what we have is kind of the rotation. Yeah. So we have kind of like that. It's like a cone, but very pointy cone, that is. Right. So the volume we know from -1 to 1, so that limit is easy to determine. It's going to be pi, the radius square, and then the width. The radius, let's call that r square, and the width is going to be dx. Of course, we're going to chop that. It's like, how do we determine the radius? To determine the radius is going from the axis of rotation to the edge of the region. So if we talk about this region here, try to. So we have that. Then we rotate about the x-axis. So the axis of rotation is the x-axis, going from that to the edge of the region. So this is just like what we did in previous section, the upper function minus the lower function. So in this case, the radius is equal to the upper function, which is x plus 1 square, and then the axis of rotation is 0. So upper function minus the lower function. Lower function is y equal to 0, the x-axis. So minus 0, so just x plus 1 square. So in that case, we have -1 and 1. Usually when we do the volume by revolution, we can just check the constant outside. The pi is the constant, and we leave that outside of the integral. The radius square, the radius is x plus 1 square, so we have x plus 1 square, and then square again, dx. So that's pretty much it. Of course, a square and a square. Is x plus 1 to the 4th dx. Right. So math option number 9, going from -1 to 1, and the function is x plus 1 to the 4th power dx. We're going to do this first. Leave the pi out of it, convert to fraction. So 32 over 5. And then we stick a pi to it. That gives us the volume of that shape. So it's kind of like a cone, but very pointy cone. Right, so that's the first example. Let's go to another one. So again, just that. Now, 2. Set up the integral that calculates the volume of the solid of revolution obtained by revolving that region bounded by y equal to square root of x minus 1 from 2 to 5. So what is the graph of square root of x minus 1 look like? It is the square root, but move 1 unit to the right. Right, if you want the table, there should be a few points. When x equal to 1, y equal to 0, x equal to 2, y equal to 1, x equal to 5, y equal to 2. So we're talking about this one. So we have that function. And then we talk about the region from 2 to 5. So that is the region R. And we rotate this about the x-axis as well. Yeah, revolve about the x-axis. So we're going to have pretty much that, but it turned this way. Yeah, so it looks kind of like that shape. Right, so and then we're trying to find the volume. By the way, when we rotate this, it will look like so it's like that. Right. So the volume, we know for sure from 2 to 5. The limit usually easy to determine. And then we're going to have pi, the radius square, and then the width in this case is dx. Simple enough, right? Now, how to determine the radius? So the radius is from the axis of rotation to the edge of the graph. So the function above minus the function below, and so the radius is going to be square root of x minus 1 minus the function below, which is 0. So just square root of x minus 1. So we're going to put that in here. I will keep the pi outside. The radius r is square root of x minus 1. And then we square that. Square and square root cancel out. A square undo the square root. X minus 1 square dx. I'll just do it by hand here. I'll keep the pi outside. Integral of x minus 1 is x squared over 2 minus 1. Integral of 1 is x. Going from 2 to 5. Right. So we're going to keep the pi out of it. And first we're going to put 5 in for x. And then we subtract where we'll put 2 in for it. So 5 squared over 2. 25 over 2. Minus 5. That's 7.5. And then 2 squared is 4 divided by 2 is 2. 2 minus 2 is 0. So that's one actually. This one go to 0 because it just equal to 0. 4 divided by 2 is 2 minus 2 is 0. So that one go to 0. We just have this, and that is 7.5 pi or just 15/2 pi. Right. So usually we leave the answer in terms of pi, and so we keep pi outside, do all the integral, and that should be it. So that is the disk method. Next, we have the washer method. So the washer, when we talk about washer, we mean like the washer in kind of the bowl, nut and bowl, pretty much. And then there's a washer. So the washer, the shape of the washer I try to draw is kind of like a donut, but there's a hole in it. But it's not going to be round like a donut. So we're going to have a circle and the outer circle, and so that is yeah. So pretty much it's just like a disk and take out a hole in the middle. So I have a big disk and a little disk, take out the middle, so this the part is hollow. So we're talking about that shape without the interior circle. Right, so pretty much we're talking about this, and we rotate. So when we rotate this about the x-axis, we have the big radius and the small radius. So if we want to find the volume, it's going to be the volume of the whole thing minus the volume of the hollow region. So I said I want the region to be script R. So in that case we will have the big radius from the axis of rotation to the outer edge. That is the big radius. And then we have the little radius from the axis of rotation to the inner edge. And the volume, in which case will be pi r squared times the height or the width. The width, let's say, call that h. So let h be the width or the height of the cylinder or the height of a disk, or in this particular we just have dx. So the volume is going to be that minus the volume of the little hollow region, be that. So bottom line, we're going to have this one. So the washer method about the x-axis, if we rotate about the x-axis, this is going to be it. So that instead of write like this, we say v from A to B pi, and then we have the big radius or the outer radius from the axis rotation to the outer edge. So the big radius and then the inner radius, little r squared, and then dx. So just have the volume of the whole region, of the whole thing, and take out the hollow in the middle. We have the volume of that shape. So if there is a hollow region, then that will be a washer. If there's none, it will be a disk. So let's say the R here is counting from the axis of rotation to the outer edge. From axis of rotation to the outer edge. And then the little r is from the axis of rotation to the inner edge. Right. Let's see how that works on the sample. Let the script R is the region bounded by the graph y equals square root of x, and then g of x is x squared. Find the volume of the solid when R is revolved about the x-axis. So first of all, we have f of x equals square root of x. So that is y equal to square root of x. And then g of x is x squared, so the parabola and so we have from 0 to 1, 0 to 1, and we rotate this region about the x-axis. So axis of rotation is this. So when we rotate, and pretty much we have the graph like this. So when we rotate, and so the question is this or washer method? So to answer that question, is there a hollow region? So if we rotate like this, from the axis of rotation to the outer edge, that is the big R. And from the axis rotation, there is the inner edge as well. So if there is an inner edge, the inner radius, if there is the hollow region, this is the washer method. So the volume equal to pi big R square minus little r square dx. This one we know going from 0 to 1 because the question say so. Right. So the big radius from the outer edge to the axis of rotation, so we subtract that square root of x minus 0. It might look silly when we write minus 0, but function above minus the function below. Later on, we might not have the graph rotate about the x-axis, but for now, just square root of x. The little radius is the function above minus the function below, so x squared, the function below is 0, so that is the distance, which is x squared. So the radius, big radius, is square root of x squared, and the small radius is x squared, and then we square that again, just like the formula says. Right, so we have 0 to 1. Again, if we just take the pi outside, and then we have square root of x squared, which is x, and x squared is x to the 4th. And when we integrate, x will give us x squared over 2, and x to the 4th integral x to the 5th over 5. Evaluate from 0 to 1. I put 1 in for x. And put 1 in for x. and then we subtract, and then we put 0 for x, we have nothing, so that one gone. So 1/2 minus 1/5 pretty much, with 3/10. Yeah, 3/10. Don't forget there's a pi, so stick a pi to it. So simple enough, right? So for the region, determine what is what is the big radius and what is the little radius. Put in formula. Pretty much it. Next, the region R is bounded by the graph f of x equal to 2x and g of x equal to x. This is even easier. F of x equal to 2x. And then g of x equal to x. Both of them are linear function. And we go from 0 to 2. From 0 to 2. So we're talking about this region here. And we rotate also about the x-axis. Later on we might have the region rotate about the y-axis or any axis, vertical or horizontal. Right. So when we look at this, we see the region between the axis of rotation, the x-axis. There is the hollow region here. Because of that, that is going to be the washer method. We know the limit from 0 to 2 though. So big radius square, little radius square, dx. Right, the width in this case dx. Right, so the big radius from the axis of rotation to the outer edge. And so 2x minus 0, so it's 2x. So big radius is 2x. The little radius from the axis of rotation to the inner function. That's so just x. Right? And then take the pi outside. And we have the radius square. Big R is 2x square. Little r is x. So 2x squared, so there will be 4x squared minus x squared. So we have 3x squared dx. The integral of that is x cubed over 3 going from 0 to 2. And 3 and 3 cancel out, so we just have pi x cubed from 0 to 2. Put in 2, put in 0. So we just have 8 pi. So it's simple enough, right? So we have to determine the region, rotate the axis, rotate about the axis of rotation. In that case, we can determine the radius, or the big radius and the little radius, depends whether we have a hollow region or not. And it will be just like that. Right. Now, if the axis of rotation, I just want to put that one more time. Now the axis of rotation is the y-axis. Is there any difference? So there would not be any difference. At P and Q be continuous functions, we have two continuous functions. One is bigger than the other, so bigger radius, smaller radius, pretty much. And then we have this bounded by the two functions, and we know the limit. And this time it is rotate about the y-axis. So the region when it is rotate about the y-axis, still the same formula though. So big radius minus little radius, and then the width is dy. Or here we have v. Now for this method there is no hollow region. If r little r is equal to 0, if there is no hollow region, we have this method. Right, it's no big deal. What important thing here is, just like the last section, if we want to use dy, all of this have to be in terms of y. So there will be no more x in this quantity. So for just note that r and little r must be in terms of y. As always, r is from the inner, from the axis of rotation to the outer edge. The little r is axis of rotation to the inner edge. Right. Let r be bounded by the region of in the first quadrant by the graph of x equal y cube. X equal y cube is like y equal to cube root of x. Right. So x equal to y cube. If we take the cube root on both sides, cube root of x equal to y. And then x equal to 4y is equivalent. I should use different color. Where's the green one? X equal 4y is the same as y equal to 1/4 x. So certainly we can graph those functions easily. Cube root of x, option number 4, cube root of x, and then 1/4 x. We don't really need the parentheses there, but so we're talking about that is the x cube, and that is 1/4x, and this is only in the first quadrant. Let's go to the table. Is there any nice values? Right, x equal to 0, so we have 0, 0, 0. When x equal to 1, y equal to 1. And when x equal to 8, y equal to 2 and 2. So we have that cube root function. So this is y equal to cube root of x, or equivalently x equal to y cubed. Next, we have y equal to 1/4 x. And again, we see that the intersection is 0, 0, and 8 and 2. So this is x equal to 4y, or equivalently y equal to 1/4 x. Right, and this time it is rotated about the x-axis. Sorry, kind of small. I guess I can hold that very close to the camera. So now, if we rotate about the first one about the x-axis, if we rotate about the x-axis, we will see that there's a big radius from the axis of rotation to the outer edge, and there's the little radius from the axis of rotation to the inner radius. So about the x-axis, the volume will be the limit of something, pi r square, big radius square, little radius square, and then if we rotate about the x-axis, it is going to be dx. If we rotate about the y-axis, it is going to be dy. So in general, we will have more general like this. Let's say where we can write a note. No. So I guess we have to write the note here. So if the axis of rotation is horizontal, so axis of rotation if it is horizontal, like the x-axis, the width is equal to dx. If the axis rotation is vertical, for example, the y-axis, then the width is equal to dy. So the x-axis is horizontal, we're going to use dx. So the x-axis is horizontal, so we're going to stack. It is horizontal, so the increment is dx along the axis of rotation. So we're going to have dx here. So don't think about rotate about the x-axis or the y-axis. Later on, it will be very confusing if you think about it that way. Think about the axis of rotation is horizontal or vertical. If it is horizontal, dx. If it is vertical, dy. That will be easier when we think about it that way. Right, the limit in terms of x going from 0 to 8. Because that's what we have for the region. Big radius from 0 to the outer edge. So either we use x equal to y cubed and y equal to cube root of x. So because this is x, so we're going to use the function in terms of x. Outer function minus the axis of rotation of 0. So that's just cube root of x. And the little radius r is the inner function. And again, we choose the function in terms of x. So it's going to be 1/4 of x. Minus 0. The reason we have the minus 0 because the distance from the axis of rotation is y equal to 0. So for y minus 0 is this distance here. I mean 1/4x minus 0. So put that in here. The volume is going to be 0 to 8 pi. The big radius is cube root of x. The little radius is 1/4 of x. And so that's pretty much it. Yeah, just integrate that, give us the volume. We can take the pi outside. So if it is rotated about the x-axis, that's what we have. Now what happens if we rotate that about the y-axis? Still the same thing though. So either we say x equal to y cubed or y equal to cube root of x. And then that graph. Either x equal to 4y or y equal to 1/4 x. And this one, it is rotated about the y-axis. Rotated about the y-axis meaning axis of rotation is the y-axis is vertical. So axis of rotation is vertical, meaning that the width is equal to dx. I mean dy. If we have the vertical axis of rotation and we going to slice it, it's going to be dy, right? Right, so the volume is going to be, and is there the hollow region. So from the axis of rotation to the outer edge, there is some hollow in the middle. So yes, this is the Watson method. Big radius, little radius, using dy. The y, the limits, easy to determine, 0 to 2. So I have volume equal to 0 to 2. The big radius is going from the axis rotation to the outer edge. Now confusing if I use this one, but from the axis rotation to the outer edge. So in that case, it is this line and not that curve. And we have y, so we have to use the function in terms of y. So it's going to be 4y. So like I said, from the axis of rotation to the outer edge of the graph, the outer edge is actually 4y. And then the little radius from the axis rotation to the inner edge is, again, we use the function in terms of y, so y cubed. Also minus 0, because the y-axis is x equal to 0. So that's what we have. The big R is 4y. The little r is y cubed. So big R is 4y. Little r is y cubed. And I'll just integrate that. Right, I said the setting up part is a lot more important, a lot more interesting than to integrate. We need to be able to set it up this. Right, more samples. There's a lot more samples. Let R be the region bounded by the graph y equal to e to the x, y equal to 1, and x equal to 1. E to the x, we talked about that in the previous section. X equal to 0, y equal to 1, x equal to 1, y equal to e, which is 2.71828. So it's about that. About y equal to 1, so like that. Y equal to 1. And x equal to 1. Rotate about the x-axis. So axis of rotation, if it is the x-axis, then it is horizontal. It is horizontal. That means the width is going to be dx. So the volume is going to be dx. Now is this or the Wasser method? So we think about this. Axis of rotation is here, and the region is way over there. Right? So from the axis of rotation to the region, there is something hollow. Right? There is the space between the region and the axis of rotation. So that is the Wasser. If there's no space in between, that is the disk. So Wasser method, big R square minus little r square, and the width dx. So simple enough, right? So on this region, what is the limit for x? And we can see easily go from 0 to 1. X equal to 1, and then that one is the intersection of the curve and the line, so it is equal to 0. Right, so the big radius from the axis of rotation to the outer edge. So that is the big radius, and the big radius is equal to the function subtract 0, which is upper minus lower. It looks silly. It might look silly now, but later on it will help you to set up the big R and little r. If the axis of rotation is not the x-axis or the y-axis. Right, little r, axis of rotation to the inner edge. So we have 1, minus 0. So that distance, upper function minus a lower function. Then put it back in here. So volume equal to 0 to 1 pi big R square is e to the x, and little r is 1. So we have e to the x square. When we have a power to another power, we multiply the exponent. So we have e to the 2x minus 1. Right. So that's pretty much it. Now the same region, but this time rotate about the y-axis. If we rotate about the y-axis is vertical. So axis of rotation is vertical. that means the width is equal to dy. So if we have the vertical and then we're going to slice the axis of rotation, we're going to have the increment, each one is going to be dy. Right, try to draw the same thing. Y equal e to the x, y equal to 1, and then x equal to 1. This time it is rotated about the y-axis. The region is here still. So since we use dy and the region and the axis of rotation, there is a gap between the region and the axis of rotation. So this is also a washer method. If it is not the washer method, we just have one radius, just have r square, and this is dy because the width is dy. Right, what is the limit for y though? So the y values, this one obviously is 1, and then we need to find that values. The function is y equal to e to the x, and when x equal to 1, so this is e to the first power, or just e. So the limit will be go from 1 to e. Those are the y values. Now, big radius, little radius, big R from the axis of rotation to the outer edge. So that is the big radius, which is 1, right? From 0 to 1, pretty much. And the little radius from the axis of rotation to the inner edge of the region. Now that's going to be the curve to this. Now, see, this is in terms of y. We have to write that as a function in terms of y. We cannot use e to the x. So to convert that e to the x, y equal to e to the x power into y, we'll take ln on both sides. Cancel out is x. So if x equal to ln of y. So this is equivalent to y equal to e to the x. So if we talk about the inner radius going from 0, the axis of rotation, to the inner edge, which is this function, but that function has to be in terms of y. So it's going to be ln of y for the inner radius. Should be in terms of y. And put everything in here. We have 1 to e pi big radius square 1, the little radius square is ln of y. So we have 1 square is 1 minus ln of y. Right. So again, at this point, later on it will be a bit more confusing, especially in the next section. But for now, for this washer method, if the axis of rotation is horizontal, the width is dx, using dx. Now the axis of rotation is vertical, the width is dy, so using dy. The next section, it will be in reverse. But let's go to something a little more interesting, because up to this point, the axis of rotation, all we do is just either the x-axis or the y-axis. Now what happens if it is more general? And when we say general, it's just pretty much just the vertical or horizontal. We cannot just say, how about we rotate around the line y equal to x? Well, a different story. Now, let R be the region in the first quadrant. The first quadrant bounded by the graph y equal to x squared parabola. And y equal to x. Sorry, kind of very small. It's in the first quadrant. So we only talk about this kind of small region there. Yeah, I think that looks better. Find the volume of a solid if this is rotated about the axis x equal to -1. So x equal to -1. So the axis rotation is this. And we rotate about this one. So the first thing we do here is to determine are we using the x or we using the y. So x equal to -1 is vertical, right? So we have axis of rotation is vertical. If it is vertical, chopping the vertical line, we're going to have the y. And from the axis of rotation to the region, there is space. There is a space in between, so that's going to be washed. Using the y. Right, now the limit for y, that is the small region, but look like to go from 0 to 1. Yeah, x squared equal to x is only 0 or 1. We determine the limit easily done. Now most important, how do we determine the radius? So remember, the way we always do this is going from the axis of rotation to the outer edge. So axis of rotation is here to the outer edge. So we're talking about this big R. So now remember, just like when we're trying to find the area, it's going to be the function on the right minus the function on the left. The function on the right on the outer edge is x squared. Subtract the function on the right, subtract the function on the left, x equal to -1. But by the way, is this correct? It will be no, because if this is dy, the radius here have to be in terms of y. So this is wrong. I did that on purpose, just to make sure that if it is dy, everything has to be in terms of y. So it must be in terms of y, because we have dy here. Right, try that again. If y equal to x squared, equivalent to that is x equal to square root of y, plus or minus, but we only talk about the first quadrant, so that's why it's positive. So the function on the right minus the function on the left, x equal to -1. So will be just square root of x plus 1. So that is the big R. How about little r? Little r is from the axis of rotation to the inner edge. The inner edge is given by the line y equal to x. Right? So to see from the axis rotation, we'll see the line first, and then we'll see the curve later. The little radius is going to be x minus the function on the right minus the function on the left. So this will be just x plus 1. That is the small radius. Just keep doing that. Luckily, y equal to x, so x equal to y. Remember, everything had to be in terms of y. This is simple enough because x is y, so y is x. So once again, have to be in terms of y. Right, put that back into the formula. We have v equal to integral from 0 to 1 pi big R square square root of x plus 1 square little r square y plus 1. That is square root of y. Yeah, this is dy. Yeah, when I put in the integral, I know right away that it's supposed to be in terms of y, so that's why it doesn't work. Remember, if it's y, so it have to be, everything have to be in terms of y. Just don't make that mistake that I do. Okay. And the little radius is y, and so yeah, so that's what we have. Yeah. So be mindful with, is that the x or dy? Just make sure that we use the right function. Right, now about the y-axis, the axis y equal to 2. So that is the case. Axis of rotation is horizontal. So the width is dx. Again, we have y equal to x squared, or equivalently x equal to square root of y, and then y equal to x. Or x equal to y, at least that one is easy. Now the axis of rotation is y equal to 2. Now, from the region and the axis of rotation, there is a gap, or this space between them. So the washer, if there's no space in between them, that's going to be this method. But we use the x here. Right, x, the region x go from 0 to 1. That's simple. Now, what is the big R and what is the little r. So the big R is from the axis of rotation to the outer edge. And so which will be that one? The function above minus the function below. The function above is 2, y equal to 2. Subtract the function below, which is y equal to x squared, or x equals square root of y. But we're going to use the one that have x in it. So y equal to x squared. So that is the big radius. Now the little radius will be from the axis of rotation to the inner edge. So we start from the upper function minus the lower function. And we put that in formula. R squared 2 minus x squared. And then little r 2 minus x squared dx. So simple enough. Yeah. So just need to determine what is the axis of rotation. Then after that we determine if we use dx or if we use dy, and that change the whole thing. If it is dx, all the function must be in terms of x. If it is dy, all the function must be in terms of y. And then the r is the vertical or the horizontal component. If it is vertical, upper function minus lower function. If it is horizontal, function on the right minus function on the left. Right, more sample. Let R be the region in the first quadrant bounded by the graph of x equal to y squared, x equal to 2, and the x-axis. X equal to y squared, so y equal to the square root of x. In the first quadrant, we can say that because it's going to be positive. So this is x equal to y squared, or equivalently y equal to square root of x. We don't know if we need to use x or if we use y. So if we're going to use dy, it's going to be y squared. If we're going to use dx, it's going to be square root of x. And x equal to 2, that is the vertical line. X equal to 2. And then the x-axis, which is y equal to 0. So we're talking about this region here. And now we rotate about the axis of y equal to -1. Y equal to -1, that is horizontal. So because of that, the width is equal to horizontal. We're going to slide that. So each one of them is dx because it is horizontal. And is there a hollow region or not? Oh, axis of rotation is y equal to -1. So we rotate about this axis. So the space, there's a space between the region and the axis of rotation. So that is the Wasser method. if it is this method, we just have big R square. Right, for x, in this region, easy to see that it goes from 0 to 2. And now what is the big R? So big R, from the axis of rotation to the outer edge, that is the big R. So the big R is the function that is above minus the function that is below, and the functions in terms of x. So above, we're going to use the function that in terms of x, so will be square root of x. You see, if this is dy, we're going to use y squared. We know that's dx, so it's going to be square root of x. That is the upper function. The lower function is just 1. I mean negative 1. That is. So do that give us square root of x plus 1. And then the little r, axis rotation to the inner edge. So it could be 0. It's the upper function minus the lower function of negative 1. So that will be just positive 1. Of course, that distance is 1. Right, put in the formula. Integral from 0 to 2 pi big R, it's going to be that. Little r square be just 1. So that's pretty much it. Yeah, of course you can integrate that, but that's not the focus of this section. The focus on this section is how to set up the formula for the disk or the washer method. So could be dx, could be dy, could be the x-axis or the y-axis or any vertical or horizontal axis. This one we have x equal to 2, so that is the axis of rotation. Is vertical. So the width is equal to dy. So if it is the vertical and this is the volume by slicing, so we're going to chop that. Each one is also vertical, so it's going to be dy. So think about the horizontal or vertical axis of rotation rather than say x-axis, y-axis, x equal to something, y equal to something. That would be too much. Just horizontal or vertical axis of rotation. Right, I'm going to draw the same thing. X equal to y squared or y equal to square root of x. And then x equal to 2. Then y equal to 0. This time we rotate about the axis x equal to 2. Right, so it just happened to be this is also the axis of rotation. Sorry, should be that. Right. Now, so it's going to be dy, right? And in this form, the region and the axis of rotation. The axis of rotation is one edge of it. So in that case, there's no space between the region and the axis of rotation. So this is going to be the disk method. What I mean by that is this is just going to be r squared and dy. There's no inner radius because there's no space in between the axis of rotation to the inner edge. So that's all we have. Right, so just need to determine the radius, by the way, also the limit. So what will be the limit? We know for sure the y values, we go from here, we go from 0. But what will be the upper limit? We know x is equal to 2 and y equals square root of x. So this is square root of 2. The y values will go from 0 to 2. I mean square root of 2. Because this point here is 2 and square root of 2. 2 and square root of 2. Now what is the big radius? Actually the only radius here. So from the axis of rotation to the edge. So we have that, the function on the right minus the function on the left. The function on the right, x equal to 2. Subtract the function from the left will be this curve. But have to be in terms of y. So we're going to use y squared. So once again, if it is dx, we use the function in terms of x. If it is dy, use a function in terms of y, which what we do here. So we have 2 minus y squared. And bottom line is this is just pi 2 minus y squared and then square. Alright, so as mentioned earlier, important things in the disk or washer method, or later on even the cell method, don't get the axis rotation throw you off. It's just vertical or horizontal. With that, we can determine is that going to be dx, is that going to be dy, and then determine the limit. Limit should be easy to determine. And then the big radius or the little radius or just the radius. The radius is always from the axis of rotation to the edge. To the outer edge will be big R, to the inner edge will be little r. In this case, we only have one r, so be that. So that is the disk and washer method. In the next section, we'll go to the shell method, and we'll review some of this as well. But that's the end of this section. Thank you for watching.